In 2006, he joined Clemson University and has been doing lots of fun science there, which we'll hear about. And then just earlier this year, he transitioned to chair of the department. So good luck with that. All right, so once again, happy to have you here.
Thanks so much. It's a real pleasure to be here and have a chance to talk science. I thought about bringing some budget slides and going over that and thought, no, it's time to break out of the mold. Now, I know how hard it is to sit through Colloquium. The lights are kind of dim. You had lunch a couple hours ago. The sugar crash is wearing off. And staying awake for 2 hours while I go through my 140 slides can be a real challenge. So I thought what I would do is start with the end and tell you what my main points are that you should take away, and then you can fall asleep and you won't have missed anything. So I'm going to try to convince you today that signposts, is my laser pointer dying? Yeah, signposts of planet formation around Herbig AEBE stars are common, and if you don't know what Herbig AEBE stars are, don't worry, we'll get into that in just a minute. And then try to convince you that the direct detection of planets around young A and B stars are very rare. And this creates a conundrum, where are the planets? I'm going to call that the planet luminosity problem, and then propose a solution using near-infrared spectroscopy to detect gas giant planets and disks around young stars. So try to convince you that this might be a way out of the apparent conundrum between the how common signposts are and how rare actual detections are. So starting with Herbig AEBE stars, they are named after an astronomer named George Herbig. He wrote this classic paper in 1959 where he defines this new class of emission line stars that are associated with nebulosity and fall in obscure regions. And so if you study young stars, some of these are pretty famous stars, AB Aurigae, Z Canis Majoris, Armand, Tiori. He defined this class. And as things are in astronomy, they tend to be defined phenomenologically first, and then defined more in terms of the physics or what's actually going on. And so they're spectral class F5 through B0. They have an infrared excess, and they're luminosity class 3 through 5. And so if you go to the Waters and Walkins review article, this is the criteria that are used to define Herbig AEBE stars. That doesn't really tell us what they are. What they are 2 to 10 solar mass stars with disks at or near the zero-age main sequence. So these are pre-main sequence, zero-age main sequence, intermediate mass stars. And so this is the kind of star that I'm talking about. These are the analogs, the intermediate mass analogs to classical T-Tauri stars. So our sun is a solar mass star. Stop me if I'm going too fast. I'm used to talking to physicists, so... kidding. I love physics. My PhD is in physics. I love physics, just not as much as astronomy. So these are the intermediate mass objects, the intermediate mass analogs to classical T-Tauri stars. And there's about 25 of these, 24 to be precise, within 200 parsecs that are well characterized, that aren't some kind of strange exotic thing. These are the all within 200 parsecs. And people have started imaging the disks around these stars. And the reason I cut it off at 200 parsecs is we want to get the things that are relatively close, that we can get nice, detailed images of the disks around these stars. And we have these beautiful images. These are the first 10, and as far as I know, the only 10 that have been published, 10 disks that have been imaged around these Herbig AEBE stars. Now, one of the things you might notice is that a really high fraction of them have spiral structure in them. And almost all of them have some kind of structure, some kind of ring. Sometimes it's hard to see. This has a ring around it as well. This is a ring system. This is a spirally system. This is a spiral system. Spiral. In fact, out of the 5 of the first 10 disks, what we've got high quality images of in this class of star has some kind of spiral structure. Now, that spiral structure is a bit challenging to explain. There's more or less 2 ways to understand how you can get the spiral structure of gas around these stars. One is we have a super Jovian mass planet in this disk, and the other is the disk is gravitationally unstable. It's self-gravitating, and it forms these spiral arms. And both of these effects can give rise to disks with similar morphologies. So this is MWC 758. It's got this very distinct two-arm spiral. And if you put a super Jovian mass planet in orbit, it's going to create that same spiral structure. And if you make this disk very massive, roughly half the mass of the star, you're also going to get this sort of spiral structure. Similarly, we have this more flocculent disk here with a spiral structure out here. And if you put a planet out there, it's a little lower mass, more like 3 to 5 Jupiter masses. You can get that same kind of spiraled structure. And if you put a big hole in here, it starts to look a lot like this. And if the disk is just slightly gravitationally unstable, more like 1/10 the mass of the star, you can get that similar flocculent spiral structure in the disk. So is it feasible for these disks to have gravitational instabilities in them? Can we rule out gravitational instabilities? So here's a set of simulations we did of disks where we looked at a disk that started with half a solar mass of material around a solar mass star at 10 to the 3 years, and we let it evolve, and we watched it accrete. And so the gravitational instability creates these torques in the disk, which lead to very high accretion rates and empties the disk very rapidly. This is the equivalent of the so-called Furore phenomena in young stars that happen. And so by 10 to the 4 years, you've lost about half the mass of the disk, and by 10 to the 5 years, you're down to about 1/3 of the mass. And at 10 to the 6 years, you still have a little more than 10% of the stellar mass in the disk. And so it's not entirely unreasonable to think that you might have disks this massive at a megayear or a few megayears. But this leads to the more flocculent spiral structure, not the two-arm spirals that we see. This is scattered light image simulations, and this is ALMA simulations of what you would see. And so it's not totally crazy to think that, well, maybe these disks are marginally gravitationally unstable. So the question, hydrogen is the most common element in the universe, and so molecular hydrogen is probably the most abundant molecule in the disk, which would be true, but it's very difficult to see because it's a homonuclear molecule. There's no permanent dipole moment, so you have to go to the quadrupole moments, which the lowest energy line is 500 kelvins above the ground state. And so the gas has to be really warm to see it. And the uncertainty is not in 500 Kelvin gas. That's stuff that's really close to the star. It's out, it's the colder gas further away. Furthermore, the lowest energy lines are at 28 microns where the disk can be optically thick. And so you're not really probing the whole disk. And so H2 is not such a great molecule to use for measuring disk masses. HD you might think is a little better. It's got a dipole moment, a weak one, but there's one there. And so you might think that would be the way to go, but these lines are very widely spaced, and that's still relatively high energy. And you're probing different parts of the disk when you look at these different wavelengths. And so you don't know what you're looking at necessarily. You don't have an independent way of measuring the temperature of the gas and converting that into a gas mass without some kind of disk model. And then your answer is very model dependent. Finally, CO, it's really nicely behaved. This first excited state's only about 5 Kelvin above the ground state, so you can excite it anywhere. That's easy to see. It can be dissociated. The abundance, elemental abundance in the disk itself is not entirely clear. You have to run some kind of thermochemical model to see where the carbon and oxygen are going in the disk. And so we're still left with uncertainties there. So what do we do? Another approach, I would say complementary approach. These all have problems, but they give us some estimate. Another way we can get at it is through the stellar accretion rate onto the star. So as material accretes, if we assume that the stellar accretion rate drops off as some power law, then we can integrate this from time t0 out to infinity, and that tells us how much mass has to be in the disk. And so we can do that, and what we get is just m dot t times this term. And if we go and look at a bunch of there should be a fit running through here. This is accretion rate versus age. And you see it's kind of falling off with time. And if you fit these points, you get eta to the 1/2, here minus 1/2. But we're not so sensitive to accretion rates down here, so you might imagine that it falls off a bit faster. Maybe it falls off as 1 over time squared. And so that kind of gives us a ballpark figure of how the accretion rate would evolve over long terms. Yes?
How are you actually measuring the accretion rate?
Great question. So for high accreting systems accreting at more for Herbig A, B stars, more than about a few times 10 to the minus 8 solar masses per year, we can measure the veiling of the bomber discontinuity at in the near UV. Once you get weaker than that, or lower accretion rates than that, then you can't see anything anymore because the photosphere is bright. And so what we do is we calibrate the H1 emission, in particular bracket gamma, against that UV excess, and then for lower accreting systems, we extrapolate with just extrapolate down. One of the big questions, and I've talked to a few of you about this, is it's not entirely clear how reliable that extrapolation is for Herbig AEB stars because we can't test it, and it's conceivable that that hydrogen emission line has contributions from things other than accretion, so that at lower accretion rates, you may find to be dominated by that. This plot is all T-Tauri stars, so these are all lower mass objects, and here the primary way is veiling in the blue end of the spectrum. So these are M and K stars, and any flux that you measure in the U-band, for example, is accretion luminosity that you can then convert to an accretion rate. Good question. But we would expect, if this is how things evolve, that disks are disks, and so we would expect them to evolve similarly. And so if we do that, what we get is we need to know the age and the accretion rate, and accretion rates are variable, and not all of the disk mass accretes, so you're getting really a lower limit on the disk mass. But when we do that, what we find is that the typical, so these are the nearby Herbig AEB stars. The gray bars don't have any imagery data yet. The black bars have imagery data, but they don't show spiral structure. The green bars show multi-spiral arms, and the blue bars show two-arm spirals. And what we find is that the typical, these things are sort of centered around a tenth of a stellar mass for disk mass. So it's not inconceivable that there's enough mass here for these multi-arm spiral disks to be driven by gravitational instability. That doesn't help us with the two-arm spirals. Those, because that phase is so short, the likelihood of us actually detecting it is basically zero, and it's highly unlikely. In fact, I can't think of any physical way you would get the disk to stay that massive to the age of for a 2 solar mass star to become an A star. It would be long gone by then. So when we look at these simulations, we can say the flocculent spirals, the multi-arm spiral disks, those perhaps could be driven by gravitational instabilities, but the two-arm spirals, those really can't. The only thing we're left with is planets. And it just so happens, a decade ago, we detected planets around these, well, it's kind of hard to see, as planets are hard to see. But there's some red dots here. It looks more convincing on my computer screen. There's one right there by the B, and one by the C, and one by the D. And those are the planets around HR 8799. This paper was published in 2008. This is Beta Pic, and here the planet's easy to see. It's this big white blob, and that was published in 2010. This was before GPI and Sphere were put on telescopes, and so there's a lot of excitement about all the planets we would find, because with these older instruments, they popped right out, so they must be pretty much everywhere. And again, our expectation is something like, 2 out of the first 10 you look at have two-arm spirals, so 20% and maybe 50%, excuse me, have these. Now, Johnson et al., what they looked at is post-main sequence intermediate mass stars, and did a radial velocity survey, and also detected gas giant planets, and found that the incidence of gas giant planets close in increases with stellar mass. And so again, if we extrapolate out to larger distances, we might expect that there's lots of planets out there at large radii. So 10 years later, looking at 140 intermediate mass stars, here are all of the detections so far. This is from Nielsen et al. 2019, so as far as I'm aware, this is the most current. Beta Pic has a planet, 51 Ari has a planet, HD 95806 has a planet, and HR 8799 has at least 3 planets. And it doesn't look better with the red added in. That's where we are. And so 140 stars later, these are all young, nearby A and B, or FA and B stars, so more than 1.5 solar masses. So where does that leave us? Well, 2 out of 10 show 2-armed spirals, so it suggests something like 20% of intermediate mass stars should have a planet from 30 to 300 AU. Bowler et al. 2016 and Nilsson et al. 2019 say pretty much the same thing. About 3% of main sequence A and B stars have a super-Jovian mass companion in the same range. So yes, it's small number statistics, but 20% is a lot bigger than 3%. So we've got this dichotomy that we'd like to understand. Another way to visualize this is this nice figure made by Jehan Bey showing some of the planet detections that have been done with different techniques, microlensing, transit on the ground, radial velocity, Kepler. Here's the solar system planets. And then here are the ringed disks, and then here are the spiral disks, and where the planet would have to be to explain that structure. And so we haven't looked at very many disks, and of those that we have looked at, this is Titari and Herbig AB disks and all of this. Of the few that we've looked at, lots of them show this spiral structure. So signposts say the planets are common. Looking for the planets says the planets are rare, and so what do we do? Well, part of setting your detection limit is determining how bright your planet should be. And how bright your planet should be depends on the formation history of the planet. And so this is a set of plots. I just picked this one from Marley et al. 2007. There's lots of papers that have been, a lot of work that's been done on this. The solid lines are cold start planets. So these are planets that form cold. That means that as the material accretes from the disk onto the planet, the accretion energy is all radiated away and it's cold material going into the planet. Hot start means the planet starts hot. Essentially, you can think of it as that accretion energy, instead of escaping, goes into the planet itself and puffs it up, and then the planet has to cool over a long time. And so it's much brighter than the cold start planet. Now that energy doesn't just disappear, it's got to go somewhere. So whether you're a hot start or cold start, that energy has to get out. And so we have this amount of energy that somehow needs to leak out. And so you might expect if the accretion energy is released as the planet's forming, and so the planet forms cold, that then when it's really young and in the process of forming, you might have very bright accretion events that occur. And so looking at disks with forming planets in them should result in lots of detections. And we have about 40 disks that have been imaged deep enough to detect an accreting planet. And here's a picture of all of the bona fide detections that people all agree on. We've got PDS 70, so 1 out of 40. Now there's other candidates and people disagree on whether you're looking at a disk or a blob in the disk or a planet. This is the one where I think everyone agrees this is definitely a pair of planets in this disk. And so after looking at 40 disks or so, to only have one that's clear, obvious detection raises the question is, where is all of this accretion energy? So where is all of this energy coming out? We should be able to see it in these younger phases, and we're not seeing it. And the answer, I call this the planetary luminosity problem. The answer may be that the solution is similar to the stellar luminosity problem, and that is that you have episodic accretion where it goes through these phases where the accretion is very high and it's bright for a short amount of time, and then it fades back down. And you can imagine what happens is this disk that forms around the planet, we'll call it the circumplanetary disk, is shielded from the star by the circumstellar disk. And so it's not being irradiated, it's not ionized other than from the ISM. And so it's basically a dead zone. And so material gets added to the circumplanetary disk, and the mass builds up and builds up and builds up until it becomes gravitationally unstable. And then those torques cause it to accrete violently and very rapidly onto the planet, making it bright for a brief amount of time. And then it loses its mass, cools back down, and starts building up that mass again. And so Steve Lubau and Rebecca Martin have run a series of hydro simulations showing that this sort of thing can occur. And if we put it into a disk model, then you expect this to be somewhere between roughly, let's call it 1% of the time it would be in this outbursting state. So if I wanted to go and detect forming planets through direct imaging, I only expect 1 in 100 to show up. And so that means if every single disk has a planet, I need to look at 100 or so of these before I'm going to see anything, and or know that I should see something, and so on for whatever you think the statistic should be. If it's 20%, you've got to go to several hundred to build up your statistics to say that, yes, this is what's happening. And that's hard. The other challenge is when these undergo outbursts, it isn't really a planet, it's an M-star in the transition disk. So this model that's plotted on top of it is a model from Xiaowan Zhu, who models F-Uori stars. He ran a suite of models applied to circumplanetary disks, and as you can see, it's in pretty good agreement. This isn't a fit of some grid. This is just one of his models that we slapped over the data points, and it's a pretty good fit. And it turns out that active accreting disks look a lot like M-giants, which is what you would have here. And so we're not making the claim that we've proven that this is actually a planet and not a star. It may, in fact, be an M-star. Rather, what we're showing is that these things are really bright, which they can be. They can be upwards of 1/10 of a solar luminosity or even a solar luminosity. They might look like M-stars, and so we have to be careful about how we interpret those data. And so depending on what the accretion rate is, these are different curves, what the model would look like. This is a cold start planet with no accretion. And this range of gray bars is our sensitivity for all of the published observations of high contrast images of disks. And so there's quite a bit of cold planet and low accretion rates that can hide below our detection sensitivity. You might also note that the mid-infrared is advantageous for these things. Okay, so where are we so far? The key points: indirect signatures of super Jovian mass planets from 30 to 300 AU are extremely common. So the first 10 we look at, 5 of them have spiral arms. At least 20% or 2 of them are 2-arm spirals. Direct images of super Jovian mass planets over the same range are extremely rare, only about 3%. Other physics driving the 2-arm spirals? Probably not. This is probably not gravitational instability, which points to the cold start. Now, that's not to say, in the case of beta Pic and HR 8799, the thought is that those are hot start planets, and they may very well be, but they're also atypical in the sense that we detected them a decade ago and then haven't found anything since. And so it may be they're they're sort of an exotic kind of planet that's been observed. So maybe it's cold start. And we just have a lot of planets hiding below our detection sensitivity, which means that the accretion energy should be released, making forming planets bright, but the detection of forming planets is rare. And so maybe episodic accretion accounts for this. Okay, so this is where we're at so far. So what do we do? Just throw up our hands and say it's too hard, because to get 500 disks, we would have to go out to very large distances, and you can't do that with 8 to 10 meter class telescopes, so we're done. I want to see if I can make the case that using high-resolution infrared spectroscopy gives us a tool for identifying young disks, disks around forming planets, circumplanetary disks. So here are the primary observatories I use: Gemini South, IRTF, the VLT, and Keck. I use high-resolution infrared spectroscopy, particularly the low vibrational CO emission lines at 4.7 microns to go and look for gas. This complements ALMA. ALMA is incredibly sensitive to dust in the continuum and cool gas through rotational lines of CO. But the oscillator strengths for low vibrational lines are orders and orders of magnitude stronger. So if you're hot enough to populate them, you're much more sensitive in the infrared to gas. And so this is what we're looking at, is the warm gas in the inner part of the disk. Now, one of the challenges for looking for circumplanetary disks in the continuum is that as planets form, they create a pressure bump of gas, and that traps the grains in the disk. They don't migrate in. And so that grain trapping leads to severe depletion of refractory elements interior to the orbit of the planet, and presumably the circumplanetary disk that forms. And this can lead to the so-called lambda Boo phenomenon. So you can imagine if you have a regular disk of gas and dust and you accrete onto the A star, that material you accrete is going to sit on the surface of the star and it's going to gradually sink into the bulk of the rest of the star. But that takes a while. If you were to put a planet in here and trap the grains so that the material that comes inward is depleted of grains, then the gas that gets accreted on here is going to be maybe solar and volatile elements, and then heavily depleted and refractory elements. And this abundance pattern is the lambda-Boo phenomenon. And here's a plot of the gas-to-dust ratio versus age for a bunch of different Herbig AEB stars, in which the open disks are the transition disks, and the closed circles are the what we'll call full disks. And what we see is up here, the transition disks, with just two exceptions, really have very high or very elevated gas-to-dust ratios. So if your dust is depleted by a factor of a few, then you might expect that your circumplanetary disk is going to be difficult to detect in the millimeter continuum because that dust isn't there to detect. So the other challenge is if the dust isn't there, dust is a very efficient coolant. It can cool the gas. And the gas, when there's not much dust around, can be much hotter than the dust that is there. And so this is actually a model of a Titari star. This is a vertical cut at 1 AU. We're plotting the gas temperature. Don't worry about the different curves. They're for different amounts of mechanical heating, but just the overall pattern here. The gas temperature is much, much hotter than the dust temperature. And it's not until you get pretty deep in the disk where things are dense that the dust acts as the primary coolant and cools the gas down. So you get this hot atmosphere, and this is how we see the emission lines in circumstellar disks. So in circumplanetary disks, if the gas-to-dust ratio is 500 instead of 100, you might expect this to be an even more extreme case where you get very hot gas. So how do we probe that gas? I've already said molecular hydrogen is really tough. Water can freeze out and it gets associated into OH, which has all these extra degrees of freedom, so you get these forests of lines that kind of blend in. In case of water, maybe form a pseudo-continuum. So CO, it's robust over a large range of conditions. It freezes out at a relatively low temperature, and it's very sensitive to gas that's 1500 to 500 Kelvin, this kind of range of temperatures, which is well matched for a circumplanetary disk, as I'll show in just a bit. The expected temperatures in these circumplanetary disks are on order of 2000 kelvins. So these are the observatories and the spectrometers that we use. Still some old 20-year-old instruments like Phoenix on Gemini South. Some of the data I'll show is from this. CryRes, which is in the process of being upgraded this next semester, should be made available. iShell on the IRTF is a relatively new instrument that's a wonderful high-resolution spectrometer. And NearSpec on KEC2, which was recently upgraded, which is also a terrific instrument. And so if we want to use these instruments to go and look for a circumplanetary disk, what are we looking for? So this is a snapshot of a simulation by Judith Shugali. She's done these 3D hydro simulations of circumplanetary disks. And this is the circumplanetary disk in here. It's kind of embedded in this larger circumstellar disk. The star would be right here. And you can see they're intrinsically 3D structures. And so we're looking for the emission in here. And the flow is vertical onto the disk, and that heats the gas to really high temperatures. So the size of this disk is typically of order 0.2 to 0.8 times the Hill radius. So for a 5 Jupiter mass planet, 10 AU from a 2 solar mass star, the Hill radius is about an AU. So we're talking about radii of 0.2 to 0.8 AU at temperatures of 2000 kelvins. So this is from Konstantin Batagin's paper on planetary rotation. He has this schematic of a circumplanetary disk, or maybe circumplanetary envelope. Material falls in, and beyond some radius, it goes into a decretion disk and flows outward and kind of gets recycled. And interior of a certain radius, it flows in. This is a Keplerian supported disk here, and somehow it accretes onto the planet. Now, whether that's magnetic accretion or not remains to be seen. That's what his paper was about. I'm mainly showing this just to give you an idea of what we think the structure around the system looks like. So this mess is what we're looking at. The planet's an insignificant contributor to the overall flux. When we're looking at the gas, we're seeing the gas that gets heated by this material flowing in. It gets hot, it radiates its energy away, and we're looking for those lines. So how do we do that? We don't have high spatial resolution, so we're going to use high resolution spectroscopy as a surrogate for that spatial resolution. So you can imagine if you have a disk that's tilted, and the disk, these different colors correspond to isovelocity contours, where each band, this yellow, would correspond to these velocities here. And so if it's a Keplerian disk, you get this nice double-peaked structure. And so this allows us to go and measure the gas in the disk and characterize how that gas is distributed. Now we get an extra lever from something called spectroastrometry. So here is the image of CO emission lines from a disk where the continuum's been subtracted. And you see this sort of structure in the line. What you're seeing is the blue side is shifted one direction along the slit, and the red side, this end, is shifted the other direction along the slit. And so we have this sort of S-shaped structure where we're measuring here the center of the PSF as a function of wavelength. So this is what gas in an axisymmetric circular Keplerian disk should look like. So if we have something that breaks that symmetry, we can pick that up either in the line profile and or the spectroastrometric signal. So that helps us determine where the emission is that's breaking the symmetry in the line profile. So we looked at a disk, HD 100-546, largely because it's one of the brightest Herbig AEB stars. It's 110 parsecs away. It's got a huge disk with a big hole in it. This is an image with Hubble from back in 2001. This was a STIS image. And this is a simulation from interferometry data. I think MIDI and Amber, I think, was combined to get that little, was it Amber, the 2 micron, and MIDI, the mid-infrared, I think. So MIDI gave us this, and Amber gave us this. And so we've got this little tiny annulus of hot dust, and then this large inner hole. So this is HD 100-546. And we look at the CO, and when we align the slit with the semi-minor axis of the disk, then we don't see any spectroastrometric signal. So, and the reason we don't see any spectroastrometric signal is because at 0 kilometers per second, there's emission on both sides of the PSF. The PSF is running this direction. And so this red is also symmetric, so the center of the red light is right along the dashed line, and so forth, and so we see this flat structure, exactly what we expect to see. When we rotate the slit so that the slit is aligned with the semi-major axis of the disk, then the blue end, this light that gets dispersed, is shifted spatially this direction, and the red side is spatially shifted that direction, and we get this sort of S-shaped curve. Okay, so this is how spectroastrometry works. When we took the data originally, my colleague observed this star as part of commissioning data, and the slit for Phoenix is, the default position angle is 90 degrees. So that's what we had. So this is how it's oriented relative to the disk. That's just what luck gave us. And this is the line profile. This is the spectroastrometric signal. Nothing too exciting. We didn't know about this data, actually, because we forgot about it. We reobserved the star in 2006. Sometimes sloppy bookkeeping can be to your advantage. And when we took the data, my colleague said, you know, I think I observed this star before. Let's just see how the lines compare. And what we found was that the red side of the line had gotten brighter than the rest of the line. And so we thought, that's kind of strange. And we plotted the spectroastrometric signal, and instead of seeing this dip over here, it was just kind of flat, which is also kind of strange. But if I put a source of emission right here, it's going to pull the center of light of this velocity contour closer to the center of the PSF at 6 kilometers per second. So maybe there's a bright spot of emission right here. And I thought, well, that's kind of interesting. Let's follow it up. And so we did, and this time it was brighter, but it was centered on the line. And the whole line was kind of pulled up. And if I put the source of emission, right here, it's going to pull the zero velocity, and if it has some width to it, and that's resolved, it's going to pull those contours up as well. So this gets pulled up, and this gets pulled up, and the whole thing gets pulled. So if I put my extra emission here, this is my model fit to the data. So we thought, well, maybe we're onto something. Let's go observe this with CRI-RES on the VLT. It's a higher resolution spectrograph, higher signal to noise. How does it do? Well, now it's blue shifted. Now it's on the blue side. And we look at the spectroastrometric signal, and sure enough, we've got this nice spectroastrometric signal. It's more extended here. It's back to where it started with here. And here is where the emission is getting pulled here. And so over this decade or so, we went from our initial line to a red excess, to an excess at 0, to a blue excess. And the spectroastrometric signal got pulled in different ways, consistent with a point source of emission orbiting at the inner rim. So if this is right, eventually it should move back behind the near side of the disk. And so we followed this up in 2017. And sure enough, it went, so this is the red, 0, and blue, and then there's nothing here and nothing here in 2017. And the spectroastrometric signal looks like it did back in 2003. So it's moved back behind the near side of the disk. Now, we also observe hot band CO lines, and those, if you're interested, I can talk to you about later, but those are excited through UV fluorescence, which requires an enormous emitting area. So any point source of emission in that inner rim is not going to contribute to those. And what we see is those lines don't vary. They're constant over each epoch. And so that, since they fall in the same order of the spectrum, the same basic wavelength, we can use those as a fiducial line profile to see if what the variation in the line profile is an artifact or not. So this is the picture that we have of this emission that's in orbit around the inner rim of the star. So now it's behind the near side of the disk. It should be there for another 14 years or so, and then about the time the 30 meters come online, we'll be able to go and try to image the source when it comes out, assuming I'm not retired and doing something else by then, living on a sailboat or something. So we have now 8 sources that we've targeted that we think we have a good shot at seeing something similar. So we're monitoring those 8 sources. Nothing to report yet, other than we've got some very nice line profiles that we're fitting. There's a second effect that can give rise to a spectroscopic signal, and that is as the planet orbits, resonances within the orbit drive a local eccentricity in the disk. And the orientation of this eccentricity rotates very slowly, about 1 degree per 100 orbits. So when the disk is eccentric, it's eccentric in the vicinity of the orbit, and then it drops off, the eccentricity drops off very rapidly. This is disk eccentricity versus distance from the planet. So the planet's at 1, and then it falls off accordingly. And so the line profile you get from that, from an eccentric annulus, is this sort of H-shaped profile. So the double peak profile here in black is a circular disk, and this red, which isn't really red, this H-shaped signal here is for an eccentricity of 0.2. And so we've got several disks that we've been monitoring and that we fit. So we have this asymmetry here, and so these are all lines that don't vary. This isn't a Herbig A/B star. Ci Tau is a classical T-Tauri star, but it has a 12 Jupiter mass planet, brown dwarf, orbiting on a 9-day period. And we see this asymmetry on the red side. Here, it's a weak asymmetry here in the wing, and here in the wing, and here it's a more distinct asymmetry. Most of the emissions coming from the inner rim. And then these two are symmetric. There's no sign of any asymmetry, so we don't see it all the time, which you don't expect to because it depends on your viewing angle, whether you would pick it out, even if there was always a planet in all of these. So these all have large inner holes, so we would expect some sort of massive companion in there opening these holes. And 4 out of the 6 so far, we see these asymmetries. And so the power of this tool is you don't need spatial information to get this. You just need photons to get a spectrum. So if you're sensitive enough to see the disk gas, then you can pick out these asymmetries and statistically get an idea of how many gases you need. To drive the eccentricities you can measure, you need sort of 3 to 5 Jupiter masses. When you get down towards a Jupiter mass or so, you don't really get much eccentricity. And so you're probing large companions when you see this effect. Okay, so if I haven't totally lost you, the remaining open questions, when we look at this CO emission, are we seeing a bright spot on the circumplanetary disk, caused by the companion, some sort of back reaction, or are we seeing the actual circumplanetary disk itself? From our data, we can't say one way or the other. And so in 14 years, when we have the GMT working in a nice high-resolution spectrograph on it, we'll get even more precise spatial data, and we might be able to distinguish those two scenarios. Is such a mission relatively common? This is an open question. Do we see this in other sources? The answer is we don't know yet. We're looking at that. What is the structure of these circumplanetary disks? We have simulations. Is there some way that we can tease out what the temperature of that gas is and if it's consistent with the shocks and the infall of material that the simulation suggests should be happening? And then that monitoring of emission disks is ongoing. So to go back to my summary, and I'll close with this, indirect signposts of planets around intermediate mass stars suggest that superjovian mass planets are extraordinarily common, at least 20%. Direct imaging surveys suggest that giant planets are very rare, a couple of percent. There's a discrepancy there. It may be that that discrepancy is solved with episodic accretion. If so, you need a really large sample size in order to confirm that. It may be that looking for the circumplanetary disks using infrared spectroscopy is a way to go and infer the presence of superjovian mass planets independently of these other signposts to confirm the presence of planets in the disks. And so with that, I'll close.
Thanks for that great talk.
We have some questions.
Hi, fascinating indeed. I have a few questions. I'm going to start with the. You have masses for the giant planets. Do you got that masses with radial velocity detections? And my question is if the presence of the disk and mass of the disk will influence the orbital motion that.
Yeah, so the mass of the planet, are you talking about here?
Well, yeah.
So these are just simulations. So these aren't measurements. So the structure of this depends on two things. The mass of the planet also depends on the viscosity of the gas in the disk, which we don't know. So in principle, if you knew the very precisely the mass of the planet from, say, radial velocity measurements, and you measured the eccentricity very precisely as a function of radius so that you knew how it fell off, then you could go and try to back out something about the viscosity of the gas. But these are just models. That's not measurements of planets.
I have another question.
Sure.
When you show the images of the direct imaging of the disk,
Uh-huh.
and you show the spiral structure, I'm wondering about the reason of this, on how common is the spiral structure, if an external perturber like binarity or stars in clusters can affect this.
Yeah, so these are all isolated Herbig AB stars, so they're not in clusters. And there are other Herbigs, but they're wide binaries, and so we threw those out because of those effects. So these, as far as we know, they might be close binaries, but they don't have a Y companion as far as has been imaged. And so the probability of, say, a flyby is pretty low. To get 20% or 50% of your disks to have spiral structure because of that is pretty unlikely. And so, but you're right, that kind of effect can give rise to spiral structure in general. Good question. Yeah.
Cutting off the factory elements from getting in. So, do we have any evidence that such stars do have planets orbiting around them?
Yeah, so that's a great question. We don't have. In here somewhere. Okay, so the reason I'm bringing this up, so for, let's see, let's see where I find it. I think it's this one here. It's kind of still hard for me to read. 142527. There's definitely a companion in there at about 10 or 15 AU. The argument is that it's an M dwarf, but that's what's opening the hole in the planet, cutting material off. All of these with open circles have imaged gaps in them, millimeter gaps that have been imaged. So we know the millimeter grains are not moving in all the way. And there does appear, in all of these we measure low vibrational CO emission close into the star. So the gas is getting in and dust is not. So there is evidence of dust trapping and hot gas. There's not direct evidence yet. There's sort of indirect evidence I showed of planets being in these systems, but so far we haven't imaged the planet that's inside the gap yet for any of these, with the exception of 142527, which is a different kind of beast because it might be an M star that's opening the hole there.